Hey guys, AP2, fluids in motion. We're going to talk about how fluids act when they move. So up to this point, fluids have been static. Now they're going to start moving. And we're usually talking about, air and water, right? So to get us going here, the fluids that we work with are usually in physics land, which means everything's perfect. There's no friction and things like this. So a lot of the fluids that we deal with are going to exhibit what's called streamlined flow, and that's where everything is perfect and there's no friction, and each little particle has its own little pathway, and all of the other particles are following right behind it, and everything is perfect. And we call this streamlined flow. These are the assumptions that we're going to make when we're doing problems. All of our fluids are going to move with streamlined flow, and everything's going to be nice and pretty and perfect. Fluids are going to be incompressible, which most of these problems, when it's incompressible, it's going to be talking about a liquid of some sort, because we all know that gases are, in fact, well, maybe we don't all know, but you need to know that gases are compressible, which means we can take a gas and shove it into a smaller space, right? For all the problems that we do, the fluids are going to be incompressible. They're probably going to be water or something like this. And we say that because there's this streamlined flow, there's no internal friction. So you have these two types of flow, turbulent flow and streamlined flow. This shape is important as far as our lives. This is what I would call an airfoil, and we have a fluid that's going around both sides of it. So if you're going to be a pilot, then you need to know how fluids work. When you have streamlined flow, then you have these nice, pretty lines that represent your fluid going past. Turbulent flow is when you get a lot of eddies and you get friction. Well, not so much friction, but you just have air that's tumbling in on itself, and sort of competing forces, let's just say. Some of the videos that I've had y'all watch talk about these two things. And you need both of these at certain times, right? So if you've ever flown, and I fly usually a couple times every year, I love sitting by the wing because you get to watch the wings and what they do, and they have all these neat little protrusions, and those things are designed to either maximize streamlined flow or to create turbulent flow. And so if you're sitting on the wing and you're watching, you'll see that these things will come out and they'll go in and they'll do all this really neat stuff. And there are times when you want turbulent flow, right? If you're going to land, you need to slow down, right? So what pilots will do is they will extend these things. These are called flaps. And when they extend these, they increase that turbulent flow, right? So they're trying to create more turbulent flow to slow the jet down. This is not part of our course. You don't have to know what all these little terms are, but I just think this is important. It's a good example. So here's some verbiage talking about this. Streamlined flow is kind of this perfect flow where there's no energy losses due to friction. Turbulent flow, you're going to get friction. So most of our problems talk about things in terms of streamlined flow because we don't like friction. We don't want to deal with it. So you have these two pictures, okay? Streamlined, turbulent. Okay, so we're going to talk about fluids usually moving through enclosed systems like piping systems, things like this. So you have a pipe system where you start with a large cross-sectional area and then it gets smaller. Okay, most pipes are circular in shape, right? So if they talk about a circular pipe with a cross-sectional area A, then what is the area of the pipe going to be? How do you calculate that? You need to know this, right? The area of a circle is, you're all saying pi r squared. Pi r round, what are you talking about? I love pi. So let's say that we have a fluid and it's going through a large portion to a smaller portion. Okay, this does happen quite a bit. The first thing we'll talk about is something called flow rate. Okay. Flow rate has to do with how much mass we have moving through a certain area each second, or per unit time. This is a rate, just like speed, okay? But instead of talking about distance over time, we're talking about a certain mass of fluid per unit time, okay? And so we're going to make some jumps here. Mass turns into density times volume. And you're like, how the heck did that happen? Okay, so they're going to make some leaps here. So we're talking about mass per unit time, right? And they're saying mass is equal to density times volume, right? How did they make this leap? Well, density is mass divided by volume. This is volume here. So mass, if we solve for mass, mass is equal to density times volume. So that's what they're doing there. They are saying mass is equal to density times volume. So this is the thing. Now they're going to make another leap, and they're going to say that density and volume are equal to density times area times height. Huh? Volume is length times width times height, right? What's this length times width here? Area is length times width. So I can take this length times width and I can replace it with area. So volume is equal to area times height is what they're doing. So what they're saying is volume is equal to area times height. So density times volume is really density times area times height. Got it? You may have to go back, follow those steps. And this is all divided by time. Now what happens is when you take height and divide by time, what are you really doing? What is height? Height is measured in meters or feet. It's a displacement. What's displacement over time? It's velocity. So flow rate is the amount of mass going through somewhere, maybe through a section of pipe, every second per unit time. And when we make these math jumps, we get to this funky thing that says flow rate equals density times area times velocity. Okay, that's called flow rate. The flow rate of a fluid is the density of that fluid times the area that it's going through times its velocity, because fluids are now flowing. Okay? Okay. Now, we're going to say that the flow rate is constant at any one point because there's going to be no friction to slow any of it down. In the real world, there's friction right up on the sides between, like right where the water would meet that pipe. But we're going to say that there's no friction. So we're going to say that our flow rate is a constant. Now, in streamlined flow, the fluid is considered to be incompressible. What does this really mean? This means if you see your brother, your little brother or little sister, or older brother or older sister, and they're walking by and you're holding a garden hose with water coming out of it, what are you required to do? You're required to put your thumb over the hose. Right? And what happens? Suddenly the water squirts out faster. Why does that occur? It occurs because in streamlined flow, this fluid is going to be incompressible, which means however much fluid is coming into one end has got to go out the other end. It can't back up. It's not going to be able to compress. So if I put my thumb over the opening of that hose, I am decreasing the area of that hose. And if the area gets smaller, what happens to the velocity? It's got to go up, and you squirt them, right? Okay. We're also going to assume that the density of the fluid is the same throughout the whole pipe because everything's perfect because we're in physics land. So the density is going to cancel on both sides. So this is a before and after picture. You could have before you put your thumb over the hose and after. Okay? Does that make sense? And so what happens is we call this continuity. And what it basically says is the area times velocity in one part of your pipe is equal to area times velocity in the other part. So here's what happens is if you have a large section of pipe, then the area is big, but the velocity is going to be less. if you have a small section of pipe, then the area is smaller, so the velocity has to go up. So if you think about how cities move water, they move water through pipes. Question, is it more efficient for a city to move a lot of water through a big pipe at a slow speed, or is it more efficient for the city to move less water, only faster through small pipes? How do cities do it? Cities tend to use large pipes, and they don't move the water that fast relative to other things, right? So all of our water, all of our mains, they're called water mains, are very large, and the water's not moving quite that fast. And so what happens is, as it gets closer to your house, all they have to do is take the pipe and make it smaller, and the velocity can increase. That's a thing. It's just like you putting your thumb over the end of a hose. So here's a little practice problem. We have oil, for some reason, going through a pipe. The pipe has a diameter. You need to know what that means. It has an average speed of 4 meters per second. And they say, what is the flow in meters cubed per second, right? So what is our flow rate in meters cubed per second, okay? Radius. Pipes are circular, so the area of a pipe would be pi r squared. So if they give it to you in diameter, you're probably going to have to change to, radius, okay? Here's our velocity. So we have to solve for the cross-sectional area of the pipe. Flow rate, which they're calling R here, is equal to AV. And you just plug in numbers.